for today. So today we're going to look at a coding algorithm. I'd really call it actually like a coding challenge. And this is the kind of thing you will definitely see in interviews that you do. And one of the reasons that I wanted to do it is because it requires a lot of things that are actually really important for coding in general. And so it's, there's some controversy in the coding interview world about how effective interviews actually are, how effective making people do these algorithms are. And I would vote, at least when it comes to some things, that they are pretty effective because they require you to have to do problem decomposition, right? Which is, how do I break this down and tackle it, one manageable bit at a time? And it's, general critical thinking. You're going to be presented with critical thinking. You're going to be presented with something where it won't necessarily be immediately obvious how to solve it. In fact, it's probably going to take some reasoning about it to solve it. And compared to some of the stuff that we usually do, it's like writing an Express server. That's a little bit more mundane. It's like you know how to do that. Once you've done it once or twice, you can look up the documentation and everything. So there's this component of critical thinking. And then there's this question of code quality. So one of the things that your interviewer is going to be looking for is, how good does this code look? Is it pretty clean, and it doesn't have to be pristine, but do I understand what the variable is? And does it do things pretty efficiently, or does it go in this totally roundabout way? Is there a lot of extra stuff? Critical thinking, code quality, communication, right? So one of the things that's really critical that interviewers are looking for is, can this person communicate about what they're thinking and what they're coding? Right? Is this resonating for you? That this makes sense at least? Yeah. Communication. There may be some other things, but these are really kind of the key things that I'd want you to take away from today is seeing where you're at with these and knowing how to sharpen that. And one of the things in particular with communication is it's not just after you get done with a thing, then saying, great, so here's what I did. I made a function that did this. It's communicating in the moment. And this can be one of those things that's kind of nerve-wracking for people. And so it's one of the reasons that I highly recommend you practice doing this thing, which is coding and talking at the same time, or at least thinking about something and then talking about what you're thinking about, so that the interviewer isn't sitting there for 15 minutes just kind of in silence while you do something. They're able to follow along with your process, right? So I really hope this serves kind of multiple purposes, that it gives you a benchmark for where I'm at for interviews, but also a benchmark for where I'm at with these kind of meta skills, and I hope it's kind of fun. I'm going to show you an algorithm that I would say is on the kind of medium easier side, and don't be daunted if it seems hard, because one of the things is when you first get into these, they can seem pretty hard. And once you've gotten a flow of like, how do I approach this? How do I break it down? What kind of functions am I using? How do I manipulate strings? Like once you get more comfortable with that, it'll seem easier, I think. Sound good?
Yeah.
Mm-hmm. And so the way I would like to do this is I'm going to put this up, and there'll be an open file where you can complete the challenge. And there are two keyboards up here. And I'd like to see if it works to just kind of tag in and tag out, that at any given point there's at least one person up here, but preferably two, and they're talking to each other about what's going on and talking to the group about what's going on, and that at any point someone else can stand up and tap somebody on the shoulder and tag in, right? And don't be shy about doing that. We're all learning here, right? So, and if I'm standing here, are you guys able to see
Yeah.
Cool. So here's the challenge. Check permutation. Given two strings, write a method to decide if one is a permutation of the other. Right?
What does permutation mean?
Yeah.
When two words, like you have two like strings, and they're the same one, they have the same string,
Say it again.
and they may be in different orders.
Say it again.
Like given two strings, they have the same length and they have the same letters in the string. They just may be in different orders, right?
Mm-hmm.
Yeah.
Yep. And so this is one pro tip for interviews that also translates to coding and coding specs and everything is become very clear up front what you're doing and check your assumptions. So what would be the worst is if you came into this thinking that a permutation was some other thing, you coded some great algorithm to do that thing, and then you got done and the interviewer's like, what's going on here? So always okay to ask clarifying questions. There may be something that the person says like, I'm not going to tell you that, but most of the time, like even if you said, I guess I'm not totally sure what a permutation is. Can you help me with that? Or I'll tell you what it is, and can you tell me if I'm right? Those kinds of things are usually fine. So yes, a permutation would be if you had ABC, ABC, permutation of that would be AA, BC, BC, right? So same letters, but in a different order. So who wants to come up here and take a whack at reasoning it out? Go ahead. And I may make some notes over here or some comments as we go.
All right, so, hey. So it looks like we have two strings here, and we're trying to check if that string is a permutation of the other. And we've talked about like a permutation of this string will be of the same length, and we'll have the same characters, but in different orders. So what I'm thinking is if we just sort both of the strings and compare those strings, right? If it's the same string when we sort it, then it's a permutation. If they're not equal after we sort it, that means it's not a permutation. Yeah, does that sound like a good attack? Yeah. Okay. Okay. So let's try it. Okay.
The one that's making I forget what it is. It was kind of inspired by Brita's editor that she had a couple months ago.
Oh, that's not part of the
Very exposed, Justin.
Brita just had this really great thing where when she would type, it would make these like animations in her editor. And I saw it, I was like, this is so cool. So I found like a kind of different version.
All right, so what I'm going to do is I'm going to make two words that are going to be the sorted version of word 1 and word 2. So sorted word 1 will be word 1. Because we can't really sort a string, we would have to split that to make it into an array. Then since this is an array, we can sort it, and then we can join it. To make it a string again. We can do the same thing for the second word. And then we can return if sorted word is equal to sorted word 2. Does that look?
So your joins.
Should we write a couple test cases for this? Okay, so let's say let output equals check permutation. Oh, nice. ABC.
Not like where is this?
Yeah.
So this should be true.
Yeah.
Okay, how do I run this? Is there.
So click this little plus. And you're in the algorithms folder, so you should be able to run the file.
Okay, so it's node. That is true. Let's try if we say that's false. Yeah. Yeah.
Cool.
Okay.
So what do y'all think?
I have a thought,
What's that?
which is that my initial thought of how to do it was different, and I like yours better. And what that makes me realize is that in the planning stage before I start coding, what I might want to do is like, okay, cool, I have this first thought, maybe like, write that down, like in a comment or something, and be like, that's one way, and then be like, is there an easier way though? Is there like, cool, I got one, but like instead of, like I do know that you don't want to like overly optimize too quickly, but like just because I got one way of doing it doesn't mean that I should stop thinking about if there's an easier way.
How do you want to do it?
I was going to, which one? No, help me remember. I was going to essentially do some sort of like a loop within a loop to check and see if every letter is being used once and only once, which is possible, which is doable, but his way just makes more sense and is cleaner, and does a little. It is, I think, a little bit more time efficient too than doing a loop within a loop. You get what I mean when I say loop? Yeah.
Yeah, and that's a loop, right? And that's a loop inside.
Yeah, exactly.
So how would the nested loop work?
It was going to be like turning them into arrays and then doing like looping through the first word and checking to see like if this letter exists inside of the second letter, and if it does, move on, and if it doesn't, then it's obviously false. And then I would have to put in some sort of error checking that like making sure that it that like it was the right number of each letter, which is why this is nowhere near as easy of a solution.
I don't think that part of what you said is a bad idea. The first thing I probably would have done is check the lengths of both, because if the lengths don't match, there's no reason to go through the rest of the algorithm. It's false. So like you're onto something.
Yeah. Well, thumbs up to both of y'all. And Lorraine.
So do we necessarily have to check for the length is just not the same as get out
Say it again.
if it's not the same length, just get out of the script basically.
Yeah, that's what Sabrina was saying.
Right?
So don't even sort it if the lengths are not equal.
Yeah, if the lengths are not equal, jump out of your algorithm. It's false.
Yeah, okay. So we'll say if word one dot length is not equal to word two dot length. Okay.
Cool. Yeah, good optimization. Something that will likely screw you a couple points.
Mm-hmm.
Now, if you want to do this without sorting?
Right.
You can use like includes. Like if you have an array, you can use include.
So with includes, I think the problem would be, yeah, if we have two A's and if you say A includes, it's still going to say A, but we're not sure if we have two A's. If I had to do this without sorting, I would probably make objects. So for, right, so that will look like, all right, there are two A's, two B's, and two C's. And if I make object out of that two, it'll be 2A, 2B, and 2C. Then I would have to iterate through both of them and make sure they have the same values. Right?
You can build the object once you do so do that.
Yeah.
Yeah.
Say a little bit more about what,
I think he's saying he's making an object and he's mapping the letter. So if he finds an A,
So this would look something like,
basically the string. If he sees an A, there's no A in the object, and an A in the value 1 finds another A.
Got it.
Replace the value.
got it.
Yeah.
yeah, something like that.
Mhm.
Yeah.
Yeah, so let's talk for a second about time complexity. Who has thinks they have an understanding of what time complexity is or what it means?
Kind of.
Okay.
Kind of. I recently found out through doing actually smart contracts with Solidity, like however long it takes if you want to, let's say, execute like not really Fibonacci, but like some kind of algorithm, like depending on the company level itself, and like depending on how long it takes to perform certain computations, it can expand exponentially on the complexity level and the length it takes to actually execute that computation. Well, this is how I understand.
Okay. Theo, what had you say, what if we had to do it without a sorting algorithm?
When I don't know, I looked at this thing and I thought about doing it with sorting. I was like, well, I can't sort. The same solution my Bob came up with. I just wanted to know what you would come up with.
Sure.
So.
Yeah, so time complexity it's kind of a thing unto itself. It would be a lecture unto itself. But one of the important things to know about it is that time complexity is different from efficiency or the amount of time something takes. So we're used to thinking of like, how long does this function take? If I ran it with this, does it take 2 seconds? Does it take 5 seconds? Time complexity is a measure of the time complexity, like the kind of, how to say it?
It ticks.
What's that?
Like it ticks. Like operations.
Not even that. So what it's saying is, how does this algorithm scale as the input increases? So if you had an algorithm that just looped through a word once, that would be what we call big O. So big O is referring to time complexity, and you'll hear this more and more. Big O of n, because n is the number, the variable that we use to mean the length of the input. So if we have an input that's length n, the algorithm scales by just n. It's linear. Okay. If you had a nested loop, right? Mm-hmm. So there's n, and then for every iteration through that loop, you're doing another n. What do you think the time complexity would be for that? N squared. Yep. And again, this doesn't have anything to do with how long it takes on a computer. You could time two functions, and they might be almost the same for normal inputs at a kind of like 1 to 100 characters. It might be just almost immaterial. But the point of this time complexity thing is to evaluate how
bad it could get.
How bad it could get, and kind of
The number of processes.
how efficient the algorithm is. So it is about efficiency, but in a different way than we sometimes think about it. So the thing to know in this case is that sorting algorithms have a time complexity of at least n log n. Okay, and again, don't worry too much about wrapping your mind around the whole big O notation time complexity thing. But n log n is, of course, greater than just n, right? And
And n log n is actually worse than n squared, right? or is it, or am I misremembering?
Better.
It's better. Okay, cool.
Better than n squared.
Okay.
Yep. So the best you can do with the sorting algorithm is n log n. And so the question is, and you might want to talk with your interviewer about this, or they might actually ask you specifically, so what's the time complexity of this? And in this case, what's the time complexity of this function as a whole?
Do we care about the time that it takes to create the memory for split and join? So would it be 2 and 11?
Well, actually, I take that back. What are you thinking about with that?
So calling split and calling join causes us to go into another function,
Mhm.
and then also demands of us that the memory space
Less than one of the
to handle whatever happens in split and join actually exists. So I don't know if that's like negligible in our time complexity.
Not negligible. Not negligible. Definitely. And so I'm glad you brought it up, because keep this in mind that if you're writing an algorithm like this and you're using some built-in function, you may be using a built-in function that, while it's quick and works for all sorts of JavaScript stuff, actually has a time complexity that is not ideal for what you're doing. You know, so you need to be aware of the time complexity of something like split. And so I don't know for sure, but it makes sense to me that the time complexity of split would be
N squared.
what?
N squared.
It would just be n.
N is what I was going to say, because to split something like that, you would just have to iterate. You have to touch each element once, or touch each character once.
And you'd also make a new array and copy those value in, right?
But it's still for each element, you're just doing one thing.
One. Okay.
So it's O and N.
So it's big O of n.
Gotcha.
So big O of n, I think the join is probably the same, big O of n. There is a separate question about space complexity. So that's how much memory this is taking up. And again, it's different from like how many megabytes. It's this question of how efficient is it, how well does it scale? Let's not go into the space complexity thing. It's once you get time complexity really well, it's easy to transition to thinking about space instead.
Mhm.
It makes sense that split has to touch each one, like you said, because it has to like search for that whatever you're looking for. In our case, we're looking for a blank character. But join, wouldn't that just be like a single action? Like you don't have to like search for anything or iterate through. It's just like
Concat each, right? Concat each.
Well, think about how you would implement it yourself.
right.
You know, if you were a library implementer and were implementing array.join,
Right.
you would take that join character, you would iterate through each element of the array, and you would create this like result string that's like
I guess
character
I would
plus-
the array, ask for its length, and then create like that query element whatever plus and all together, as opposed to saying for each one like having to look through, push into a string.
under the hood. That's what you would need to do, is loop through it. So I mean, if you can come up with a way to do that, like in one single action, do that. I'd be really interested to see that. But the thing that I'm thinking about it is there's no way for the computer to do it without touching each thing once, even if that touching is just to take it from here and put it over there, right?
So here we're saying each of these lines, each sorted word line, we're touching each thing at least 3 times to split, to sort, and to join.
All right. Yes. Yep. And then the sorting actually isn't just touching it once. The sorting is touching it and
Many
log in,
times, yeah.
right?
Is the length of the word.
So are you sure that this is n log n, or that could be anything, right? We don't know what that is.
It could be anything. So the JavaScript, you know, and it's going to be implemented different whether you're on V8 or the Chrome V8, or I think Node still uses basically the same engine, but there are other JavaScript engines, so it may be implemented differently. So it'd be interesting to look up. I would be surprised if the algorithm that they chose didn't have n log n time complexity.
I think from what I've researched a little bit is if you have a really large array, they're going to use merge sort, and for smaller numbers, they're going to use quick sort or something like that.
Yeah, I know in Python, they do a really interesting sort called timsort. And so if you want to look it up, it's worth looking up timsort Python algorithm, because it takes these different algorithms and innovates on them in a way that, you know, people 20 some years ago didn't think there was like any new way to innovate. And then all of a sudden we have this, like, it's still n log n, but it has like quite a bit more efficiency when it's running just in terms of runtime. So the thing to know about time complexity is if you have, so if you're doing one thing to a string that's big O of n, and another thing to a string that's big O of n, in math, that equals 2n, right? Because it's n plus n, so 2n. But when we're talking about big O, we take off that number. So big O of 2n is actually just the same as big O of n, right? It's not true when you're talking about exponents, so like n squared, n cubed. Those things matter, but in terms of that coefficient, that doesn't matter. So lots we could talk about time complexity, but this function as a whole, what do you think the time complexity is? Might be easier than you think. Whoever has a thought, don't hold back, just throw it out there.
N plus log n.
Okay. So,
N plus n log n.
okay. So n plus
clear on what effect throwing out log versus square is supposed to have.
Say it again.
I'm not clear on what having an n squared versus log n is supposed to be referring to. I understand if it touches each element once, that's just n. If it's n squared, it's because it did what?
It's because for each element, it needed to touch n things. So it's like if you went through one string and you compared, you know, that character to every other character in the string, that would be n squared, because by the end you would have done n squared things. Right?
Log n on the other hand is
That's like
right. But I'm saying
It's
like
just
if
it's time. It's gotta go.
it touches it once, it's just n.
To the
It has to
board.
go through and it gets like it's doing a lot more processing, I guess. That's n squared. So it's log n meaning like we're finding a way to make it less than touching it everything once.
N log n is less than touching everything n squared.
But not necessarily less than
Right.
n. Okay.
Yeah, like, let me just show you
So
this.
it's like a
This
single set of processes.
is, say it again?
Is in log in a single is log a single set of processes? I've never known this what log is.
You know how you have squared? Log is like
So here's a chart of the different time complexities. So if you have something that's big O of n, it looks like a line that goes this way. Think about this for a minute. You're designing something that's gonna. You're designing something for Google, and you know that right now when you're testing it, you can test it on just a few. You know, maybe it's something that reverses a word or something like that. And right now when you're testing it, you're just testing it on some small things. But when Google uses it, they may use it on words that are, or you know, strings that are
thousands and thousands and thousands of characters, right? So right now, it's kind of you're using it in a small case, but in the production case, it may be taking inputs that are huge. Would you rather have that have a big O of n or a big O of n squared? Why is that?
It's processes.
Yeah.
It's less processes. It's it's literally, I think I don't know. It's less processing.
Mm-hmm.
O of n is
And-
constant, right?
And in particular, as the size of the input increases, for big O of n, there's a much smaller increase in the time complexity, versus for n squared, it just shoots up. So the bigger your input gets, the more it matters how efficient how time complex your algorithm is, right? So this is telling me that it would be both fun and useful to do an entire lecture on time complexity. But for the time being, take my word for it that, so on this line, you've got word length. What do we think the time complexity is of the length operation?
And it should be 1.
It could
It's like
be,
a property of the object.
it could be 1, or it could be n, depending on the implementation. Probably true that when a string object is created, they simultaneously set the length so that they don't have to recompute it each time. So I'm gonna say it's probably big O of 1, which is constant time. So it doesn't matter how long the string is, it's always gonna take exactly the same time complexity to look it up. So big O of 1 and a big O of 1. So here we've got a split, a sort, and a join. And so we said the split is likely big O of n, and the sort is n log n. Some sorting algorithms are n squared, but most of the ones that are used in practice are n log n.
Bubble sort is that n squared.
Why, I'm so glad that you asked, and I can look up what bubble sort is. Yeah, you're right. Bubble sort is n squared. They go with n squared.
Is this sign only for JavaScript or like?
Nope. For any, this is talking about different data structure operations and sorting algorithms. So yeah, so this is good. So with an array, if you are wanting to, yeah, I guess it doesn't say anything about the length, but this is telling you for an array, in most cases, in most programming languages, the time complexity of access is going to be constant. And why is that? Because if you have an array and you want to get the 70th element, you don't actually have to go from the first element to the second element to the third element to the fourth element to get to that 70th. Because an array is this kind of fixed length thing, you can just say, take where I am and go 70 spaces down, and you can jump right to that value.
If
Right.
you search a hash table, it's a single.
Constant time. It's so awesome. It's so awesome why that is.
It's good to know.
Hash tables. So under the hood, JavaScript implements objects as hash tables, right? Because it's a hash table is you put in something hashable, like a string or a number or whatever, and then it gives you a value. So key value pairs, right?
What's the name to be hashing?
Let's talk about that later. And so what that means is to compute or to find the location of something in a hash table, you don't actually have to search through all the elements, you just have to hash it. And hashing it takes constant time, right? And so hash tables are actually used all over the place to make a lot of the functionality that we use in JavaScript, Python, and everything work. objects are under the hood, these hash tables. So super cool. I'll paste this in what's going to go up on GitHub. Check out. So finishing this up, so we've got big O of n, big O of n log n, and big O of, for join, n. Yep, I think that's right. And so the same thing on the next line. And this, so this is interesting. I was going to skip over this, but let's not. What about line 18? Time complexity there. Okay, we've got a big O of 1 constant time. Anybody else?
I want to say
Why?
well, I want to say 2n, but then n because they combine. Because I think you would have to look through each one and go like char at 0, char at 0. Are they the same? Char at 0, char at 0, and then until it finds something that's wrong and throw in there like false. So I think you would have to go through each character with each one.
Yeah, you can imagine implementing the string equality function, string equal to that string, by like for, let I equal 0, and then I, well, I is less than the string length, and then I plus plus, right? So you're going through the whole thing, and then for each character, so this is assuming they're the same length. If they're not, you would know immediately that they're not the same. For each one, you're saying string 1 of I, does that equal string 2 of I, right? And there's, if you think about it, there's no way to know if two strings are equal unless you actually go through and check the characters, right? And so in this case, it's big O of n, right? And it wouldn't even be big O of, it wouldn't even be 2n, because you're really only having to do one time through. But again, that 2n or n is the same. So if this is what we've got, and this is the part where I invite you to take my word for it, and when we get more into big O notation, we can get it. So you look for the worst offender, the worst time complexity, and that becomes the time complexity of your function. So what would that be then? Yeah. So we've written an algorithm that is time complexity big O n log n. Not too bad. We can do better.
So we're looking for, we're trying to basically not have any segments that have n log n, that only have other ones. And I would, even though it could be additional statements, as long as we don't get into positions where we're exponentially increasing our time or data as we're considered to have a more efficient function.
You're right on.
Okay.
Yep. You even though your instinct might be, well, sort is just, it's really quick. Right. It's a short, we're using it for short strings and all of that. That, I think you're getting the idea that actually doesn't matter when you're talking about time complexity. It doesn't matter if you're just using this on strings of 5 characters or 20 characters or 5,000. The time complexity is kind of on a different level from all of that. Your time complexity actually refers to the order of magnitude the order of magnitude time complexity that your algorithm has. And when I say order of magnitude, these are orders of magnitude, right? So n and 2n is not a difference of an order of magnitude. N and n squared is a difference of multiple orders of magnitude, right? So this is a different order of magnitude. This is a different order of magnitude. This is a different order of magnitude.
And one of the things I've always been told that helped me understand it is that you're assuming the worst case scenario. You're assuming that you have to
Yes.
go through like every single thing. And so that's why.
You might write a sorting algorithm that can identify a string if it's like almost sorted, and if that's the case, do just the couple operations it needs to sort it and to complete it. And that would be great. I mean, for most applications, it would be really good if you were doing sorting and if you didn't have to go through everything kind of n log, if you didn't have to do the n log n. But to date, there is not a sorting algorithm that can do better than n log n in the worst case, right? And so that's again what we're looking at is what's the worst case runtime or the worst case time complexity of this algorithm. So anyone want to take a, oh, we're almost at time.
How
Wow.
would you have done this? I'm curious.
Sounds like
What's that?
it's like just discussing or saying like hash tables give us that one or n as opposed to every squared. It seems like you would use something involving that.
Yeah.
For an object?
So a good strategy with solving these is what Danny, was it you that was saying, like, maybe this is just what I was hearing. Write something first, come up with a solution that you know will work and code that. As you know, sometimes we talk about like brute force algorithms. So even if you know it's not going to be very good in terms of time complexity, it's good to get a solution on the table. So if you have to do something that's n squared, you know, big O of n squared, and you know that going into it, good to get something that works. And then oftentimes you'll be asked to refine it. Like, hey, okay, so great. So what's the time complexity of this? And you say big O of n squared. And then say, okay, can we do any better? And you say, you know what? I think we can. And then you make some refinements. So I would have done it probably in the same way, you know, Bob, you were right on like the instinct to be like, okay, characters, so if we sort it, that should just, you know, and it's a logical way to do it. And some interviews might just end here, but probably most interviewers, if they're asking you this question, are going to be wondering if you can figure out what the more, the less time complex version is, right? And y'all were like almost there when you were talking about it, right? Anybody want to take a hack at how you would approach it, even if you're not going to code it right now? Yeah.
I would think you would go through the word one time, putting each character in an object so that you're counting the number of characters. So for this object we call word one, A would iterate up each time, but we pass an A on each character. And then have two hash tables that we could then search, I guess, any given one. If there's an A in hash table, search the other one. If they're the same, if they both have two, we go all the way through, then they're the same. If there's anything wrong, they're not. But I think that makes sense. In each operation, you're only touching all the data one time and not going to keep looping back through to complete any given operation.
What do folks think? So hash tables are useful for, I forget exactly the way we were talking about it. It's like buckets, kind of thinking of buckets and counting. And so exactly what you're saying, if we want to count the number of A's and count the number of B's and count the number of C's, hash tables are nice because you can look something up by A and then there's a value associated with it. And you can say, well, there's 0 now, but let's make it 1. And if we find another one, we look it up again and we can say, oh, there's 1, so let's make it 2, right? So they're useful for counting. And yeah, that's I think one way to do it is to use a JavaScript object and count everything and then compare what you've counted. it gets a little bit gnarly when you're at the end and you're like, okay, so how do I compare these two objects and make sure that they have all of the same thing but not anything else, right? It wouldn't be that hard, but another solution to think about, and you may want to take this and try coding this other solution, is to use an array and to look up whatever position in the array by the ASCII value of the character that you're looking at. Everybody know what ASCII means? ASCII was like a big deal a long time ago, and now it's UTF-8. It refers to character encoding. So what number does that character represent kind of in the system? Because in the underlying operating system, in text files and stuff like that, it's really a series of encoded numbers that turn into characters. So I guess I don't know what it is in JavaScript. JavaScript, look up character ASCII char code. Okay. So you said char code like that?
And then you gotta give it, if you do char code like that, then you can pass in a char, and it should give you the code.
Right.
Yeah.
Yeah.
You string it off the string and char code and give it an index, it'll tell you.
Yeah, so the solution that involves this, well, let me ask, have I told you enough that you're interested to go and implement it yourself, or do you want to hear a little bit more about that solution?
I'd like to hear a little bit.
Yeah.
Okay.
Still not sure.
Okay, so you make an array that where you look up a position in the array, and you do the same thing. You count up, for string 1, you count up how many of that character code there is, and so you'll have an array, probably like 128 characters or whatever, if you're including capital letters and lowercase letters and numbers. That is one thing that I would, one critique I would have of the group's approach is really important to clarify up front. So are capital letters and lowercase letters the same, or are they different? Are we including, punctuation and things like that? And usually, you might often get the answer that you were expecting, like, we're just using lowercase letters or something like that. But sometimes that will actually prove very useful to help simplify the problem, or to realize that you need to make your algorithm account for something that you weren't accounting for. So once you've got an array that has counted up all of the different values, I love this solution. This is not my solution. Then for the second string, you go through and do the same thing, except instead of adding 1 when you find a letter, you subtract 1. So the first time, for the first string, you're going through, and maybe the array looks like 0, 0, 0, 0, 0, 0, 4, 0, 0, 0, 0, 0, 9, 0, 0, 0, for like 4 of that character, 9 of that character, 0 of all of the rest, right? If the second string is exactly the same, if it has the same number of characters, if you go through that same array and just subtract 1 for every character that's in there, you'll go through, and when you get to that 4, it'll go 4, 3, 2, 1, 0, and the 9 will 9, 9, 8, 7, 6, 5, until the array is actually back to 0 again. So then you can just loop through that array once and see, are all of the values 0? If so, it's this idea of like counting up and then counting back down, right? And so if all of the values are 0, then we're golden. The strings are permutations of each other. If not, if there's one character that's like -1, that means there was 1 more in that second string than in the first string, right?
You can have arrays that are not 0 index.
What I would probably do is figure out the character code for lowercase a, which I'm assuming is the first, the first in that, yeah, something like that. And so then when I looked up the character code, I would just subtract 65 every time so that it was 0 indexed.
That's so pretty. I would never come up with that.
Yeah, no, I'm never.
I'm not so sure. You know, and again, the more that you do stuff like this, I mean, can't you feel that your brain is kind of like, it's like really working? So maybe we'll do this like once a week. Maybe we won't take the whole time, but to just keep that critical thinking part going.
Mhm.
It would be also if you could give us like homeworks or like instead of these kind of problems that we can work with pair for the day. You can make like a module
Yeah.
that you be like, all right, solve 10 problems today, you and you pair up.
That would be necessary. I want to kind of, that would be like cool if we had algorithms in phase 1, like a beginner, and then phase 2, and then phase 3 algorithms. I want to know what algorithms I should be like doing at this phase and at that phase as well.
Yeah.
45.
There was a thing, I was in a different group for a bit, and we did something where once we got to around this phase, every morning we'd come in and pair up, and one person would be the interviewer and the other one would be the interviewee. We took like approximately half an hour. Like one person had like 20 minutes to like do the thing while being asked the question by the interviewer. And then the last 10 minutes would be the interviewer explaining like, yes, your solution was great, or no, it wasn't, and here's why.
One of the things that we don't have anymore, which was one of like from the game was really, really good, was that we had a goal where we had to re-implement like Lodash functions.
Oh yeah.
So we that was Dev's doing, by the way. Shout out
All
to Dev.
right.
But like, so we learned like what happened beneath these methods that we use. We had like, we had one for Lodash and we had another one, but we had to it's hard. It was not easy to do that in your 3rd week. But
In your 3rd week.
yeah, I did it 3
Wow.
weeks in a row. First, second, and 3rd week, we re-implemented like 10 Lodash functions. And the one that like the flattened array, that one is like the hardest one ever. I remember I was like, oh my gosh.
Yeah. Yeah, so if you haven't used Lodash or haven't encountered it, Lodash is like the awesome Swiss Army knife of JavaScript libraries. It includes functions that are well designed and efficient and great for like a whole bunch of different things. So concat creates a new array, concatenating array with any additional arrays and or values. So you can take an array and then pass in another set of values, I guess. Flatten.
Oh my gosh. That was
Yeah, so flattens array a single level deep, or flatten deep will recursively flatten the array. I'm trying to find one that like you'll probably want to use right away because they're all really helpful. Right.
These are all like the code interview or the code templates that like make you form, and somebody just went through like made the best version of each.
Right. They're sorted into different things. One of the ones that I ended up using in a React Native app. You guys know what React Native is? Yeah, so React, but it just runs on iOS or Android. One of the ones I ended up using was Throttle. And Throttle is cool because it has a couple different configurations, but it allows you to throttle the number of times you call a function. So, so the specific case was I had some data in the application and I wanted to save it to the device's kind of permanent storage, right? So apps run in memory, but you can also write to storage to save things between times you run the app. And so I wanted to update that and keep that updated like pretty regularly, every few seconds. But what I was finding with the original way I had written things is that that storage was being asked to be updated sometimes like 20 times a second when you would like change a bunch of values or you type something in, it would be called like a bunch of times and it would slow down the whole application. So I used Lodash throttle and I said, run this at most every 5 seconds. And so then it'll run right away when you make some update, and then it'll wait 5 seconds, and then it'll it'll run again with the last call, the last like most recent thing. So not super important to understand that or even this, but just to know that Lodash has like all of these awesome functions that work really well and you can use in your code.
What's really cool is something that like Miles was pointing out is that like if you can re-implement these and then like maybe write a test for it, which we had, you can actually see if your re-implementation of these methods is faster than the Lodash.
Yeah, because I'm looking at this like, I wonder how I would do that.
And we would do that. Like you would check how fast this runs and you like run a test and see how fast yours runs. And sometimes we beat it sometimes. Like one time we beat it. like literally once. We were testing with Jasmine back then and we beat it like one time.
That sounds fun. Sounds like a
It's hard, but it's fun. And you'll learn like what's going on under the function, like how these are being implemented.
I feel like this also just gives you other ways to think about what you can do with data.
Yeah.
Because a lot of stuff I'm like, I can only use these 3 methods to manipulate this. I have to combine these together to make some hack together long function. And it's like, oh, I could have just delayed it or whatever that does and had it done like one movement. That's already super efficient.
Yeah. So maybe we'll do live coding of redoing a Lodash function. Taking us over time. I mean, I guess it's an hour from when we started. So thanks, everybody.
Thank you.
And whenever you have time for a code review for us, please let us know because we're all heading to meetings.
Oh, okay.
But we'll be back.
Yeah,
Yeah.
I can do it, I think, right now.
Okay. Cool. Yeah.
Oh.